Yes, Professor, we are ready.
Yeah. And the recording.
Yes. So we have to start recording. So welcome participants. We will be having yet another interesting session. Today, Professor Bengt is going to speak on optimization and also perhaps reinforcement.
Reinforcement comes tomorrow.
Okay. So Professor, I give it to you then.
Yeah.
Thank you.
Thank you. And hello, everyone. So today I will complete the discussion on or presentation of the temporal logic part, and then go on with hybrid systems, and that includes also optimization. And also some words on time systems, and that also includes optimization, yes. So let's so we talked about temporal logic, and maybe I should show you this slide just to very briefly repeat that we can specify now some properties like, for instance, that something is always valid, an atomic proposition is always valid, square P. That means that in a sequence of states here, it's always in all states, this is valid in linear temporal logic. And the other typical specification is that, okay, sometime in the future, eventually P will be valid. And that means that at some state you have at least one P, and after that you don't care. And also before this, you don't have any specific limitations on what could be the situation or what kind of properties that are satisfied then. Next P means that in not the first but in the second state P is true, and just P itself means that it's true now in the first state. P until Q means that P must be true until Q becomes true. So that's a bit harder than eventually P. As you can see that eventually P is actually a special case of this until, where you put, instead of P until Q, you write true until Q. And that means true here, then, and then you can put anything here, and it's considered to be accepted. And then we have this infinitely often square diamond P. That means that repeatedly P must be true. From time to time you get a P. And eventually always P means that after some time you must have always P. So that's quite an intuitive. This is a bit more strange combination, always eventually. But if you think about the meaning of that, this repeated behavior is quite natural. So then the question is how we can compute this type of or algorithmically evaluate if these type of properties are true. But before I show you that, I will also mention about the alternative logic, which is called computational tree logic. And then we say that, okay, what you do is that simply you add also a quantifier, the existence or for all. An existence, let's say we take first for all. That means that in every sequence of this tree, or it could be represent an automata, sorry. Then eventually you should get a phi in this case. Phi corresponds to P in the former description. Phi could then be a more general, arbitrary temporal logic expression. So eventually phi means that in every sequence you go down here, you get sooner or later a phi. And always, for all, always phi. That means that in every state where you go here, you have always. For all sequences, you have always phi. Here we have existence of always phi. That means that there should at least exist one sequence where you have phi. And existence of eventually phi means that it's enough that you have one sequence where sooner or later you get phi. So this computational tree logic is in some sense more detailed, but the thing is that then if you combine operators like square and diamond, always eventually, you must have these are called modalities, and then in front of every modality you must have a quantifier in CTL, which makes it a little bit more restrictive. And people have very different opinions about this. Some people say, oh, LTL is much better, and others say that computational tree logic, CTL, is better, more useful. And of course, the conclusion is then why restrict to these two versions? Why not join them into one? And then we have CTL star, which is an extension of CTL, but where you can also have these combinations of yeah, well, or you could say that you have the quantifiers, but you don't have the restrictions on the quantifiers which you have in CTL. And then last time I gave you some examples on safeness, liveness, and fairness. And then we went on with a discussion on this mu calculus, which is actually the tool which we will generate algorithm, which makes it possible to evaluate, especially CTL, I would say. So if we go back to this expression, we repeat also here that, okay, we could have different state labels on the different states, and what we are interested in is to, by this expression, say that, okay, in which states is Q true? And it's in state 1 and 2, and R is valid in state 2 and 3, as you see there. And the typical state label specifications we are introducing in this course is mainly that a state is marked, like this double circle, or that we have a forbidden state. But with these atomic propositions, you can actually combine everything you like. So what I'm going to show now is an algorithm which makes it possible to compute, for instance, the specification that there exists at least one sequence or one path where eventually Q will happen. And just to repeat what that means, we can see here that in this expression, or in this automaton, this is valid in state 1, 0, 1, and 2, because in state 0 you will eventually get Q. But in this state, eventually Q is not possible because there is no state in the future where Q is true. And then we had this new calculus operations, or we can say that mu calculus is actually an extension of both. Yeah, it's a kind of temporal logic, we can say, but it's very flexible in its description, and that means that all the known more user-oriented temporal logic expressions like CTL, CTL star, LTL, etc. They can all be described by this mu calculus. And then I gave some formal expressions both for the syntax and for the semantics. And I think that, well, I mean, it's obvious that, okay, if you should take a set operation and you have a logical expression inside, then that will be replaced by the intersection. And if you have the or in between these two, you get the union instead. So some of these basic things are quite obvious, but there are then two things that are both more powerful and also a bit more complicated. But these fixed point operations, where you have the least and the greatest fixed point, they come also out quite easily, because it's just what you start with. For the least fixed point, we start with the empty set, and for the greatest, we start with the whole set of states, and then we iterate. The complication, and I would say the only complication in this procedure or this mu calculus, is this pre-function. And I started to discuss that a bit last time, and I think I came up with a very small example here, but I think that I will go on with this one and go through that in carefully. And then I come with some additional examples later on. And we also, I will also end up showing you one example here with, you can say, planning problem, where you specify properties by an LTL description. So I would say that that is one of the great applications of this procedure. So let's see here. The question for this problem is, in which states is this property satisfied? There exists a path where eventually you get Q. And just by looking at this, we can say that, well, it's true in state 0, it's true in state 1 and state 2, but not in state 3. So yes, I mean, it's simple just by looking at it. That, okay, in state 1, you already have a Q, and you also have a Q in next state. But after this, there are no more Qs. So that means that in state 3, if you're staying in state 3, you will not satisfy this. Now, we can say that every type of temporal logic expressions, the basic ones, we can say, has a corresponding mu calculus formula. And when I give exercises and also the exams for my students, I give them a translation table from every standard CTL expression, I would say mainly, to a mu calculus formula. And then we could say that the derivation of these mu calculus formula, that is, I'm sorry to say, a bit complicated, and there are actually, I haven't found any good paper on that in the literature, although I've searched for that for a long time. And there is some procedures, but I try to understand them, but no, I cannot understand them simply. But on the other hand, for instance, in this handbook of on model checking, the big large book I mentioned to you earlier, in that in the end, there is a chapter on a bit on mu calculus. And there they have also an extended table of mu calculus formulas. And remember that when you have combinations of these basic functions with and or in between, then it's just that you take to evaluate the individual ones. So in that case, it's quite straightforward. So although I couldn't say that this is absolutely a tool which I can apply to any formula, because I'm a bit limited on that, but I think that for the most useful formulas there are procedures to do this, and I think also that in the future there should be also software which can translate any LTL expression to mu calculus. Let's go for this now. And then we have this formula saying that existence eventually Q is the least fixed point, because it starts here with mu, and mu stands for the least fixed point of this logical expression. The least fixed points for y, where y is involved in the function psi of involving this atomic proposition Q, or there exists a next state where y is true. So let's see how we can apply this. Then by these double brackets, I call them, I don't know any good name for that. Then we would like to have the states where this expression is true, and since these two expressions are equivalent, it's just to put the same notation here. And then the question is, how should we interpret this? Well, it's the states where this mu calculus formula is true, but then there is a translation of that given the semantics, where we now, instead of small y, which is a logical variable, I introduce a set capital Y. So I'm searching for the least set of states where I have the fixed point that y is equal psi of y, but now y is a set. So to make that, to obtain that fixed point is just that we will start with y equal the empty set, and then repeat psi of y, first psi of empty set, and then you get a new y, y1, and then you take psi of y1 and iterate that until you reach a fixed point. But you will soon see that. So you could say that these are just introduction, and the real stuff start here. And that is that this mu of y should be translated to a set formula, yeah? And then we take this expression and apply the semantic rules which we had here earlier. And then we apply first the or condition, which should be replaced then by union. So then we take the set where Q is valid, union with the set where existence next y is valid. Okay, this is actually exactly the description of this pre-function. So existence next y means in set expression pre-existence of y. And then the question was this pre-existence of y? Well, it's actually one step backward on the set y. So let me illustrate that soon. And here capital Y is now also the set where the logical variable y is true. The least fixed point, as I already said, is obtained by iterating yi plus 1 equal psi of I y of y of I, sorry, y of I. For I equals 0, 1, 2, etc., with y0 equal the empty set until you reach the fixed point yi plus 1 is equal to y of I. So by translating this mu calculus formula to a set expression, which we have here, then it's just to start to iterate this. And here starts actually the true algorithmic calculation. And what we see here is something that is absolutely possible to implement in a small software. This reminds me that I promised that I should also show some Matlab functions. I will do that tomorrow then. So I need to make a note on that. I had forgotten that. I will show you some simple Matlab functions which I use quite much myself. So here y1 of psi of y0 is then, remember that this y function psi of y was this. And that is what you see here again. So now we look at the states where q is true. And in our example, that was state 1 and 2. So the state where q is true is the set of states 1, 2. And that should be taken with the union of, up here. Union of pre of the empty set, but pre of the empty set is still the empty set. You start from nothing and then go backward from nothing, still give you nothing. So y1 is 1, 2. Then y2 is psi of y1. And then we see that we repeat here all the time this state q, which is always 1, 2. But now y1 is 1, 2. So then we should take the pre-existence of 1, 2. What does that mean? I said we should go backward. From state 1, you go one step backward and you get state 0. From state 2, you go one step backward and you get state 1. So if you join these two, you get 0 and 1 as the pre-existence of y1. And that's why we see here that pre-existence of y1 is 0, 1. And you take the union of that with 1, 2, and you get 0, 1, 2. And actually, we have already now got the answer, but we should also verify the fixed point. So that means that I will still make one iteration. So now I take psi of y2 to calculate y3. And then I get, once again, state where q is true, 1, 2, union with pre of 0, 1, 2. And that is still 0, 1, as it was before. Because from 0, there is no pre. So that does not add anything. So you take the union and you get the same as y2. And then we have reached what I called y omega, the fixed point. Omega is a kind of infinite notation. I could also have written y infinity. So we have confirmed what was intuitively clear, that it's the state 0, 1, and 2 that are true, that are valid for this mu calculus expression. Now I will take another situation where I also have the greatest fixed point, and I also have for all. And that is a little bit more challenging, but let's see here. I'm looking for the states where if I stay in a state, I know that this state and all future states, in this case, I will have R equal to. That's the meaning of this. And now we replace, compared to the existence of eventually Q as we had before. Now eventually the diamond is replaced by square, and that means that we're now looking for the greatest fixed point instead of the least fixed point. That's the difference between eventually and always. And then for all, that just comes here, and that means that we will later here apply the pre of set for all events, we can say. That's the meaning of this. So, and also actually it's not only that we have the greatest fixed point. I've also replaced or with and here. You could say that typically you have an and operator is combined with the greatest fixed point, and the smallest fixed point is combined with an or condition. Now we should solve this always globally R. No, for all always R. It's easy to miss the interpretation of this. This means the greatest fixed point of the psi of y function. Now, what is psi of y? It's the set where this expression is true, the new calculus expression here. So this is a set of state where R is true, intersected with pre for all of y. And the greatest fixed point is obtained by starting with the initial state set equal the whole set. So y0 is then the whole state space, which I call X at the moment. So then, and all states here are 0, 1, 2, 3. 0, 1, 2, 3. By this, we iterate and find that, okay, y1 should be equal to psi of y0. And then the pre for all of the whole state set X, what is that? Well, the pre, if you already include all states, that still means all states, because you can always go backward from any state. Since all other states are included, there will be no restriction on that. If you take the intersection of all states and the states R, then you will get R. That means 0, 2, and 3. And now comes the interesting step, because in the next step we should take then the pre for all of the state set 0, 2, 3. And here is the more complicated stuff here, and that is that in state 0, for all means that the target state 1 from state 0 is not included in y. Sorry. This pre for all requires, if I should include the state 0, then it must be that all if I go forward to to state 1. Okay, the rule was that a target state from state 0, all target states from this must be included in Y. Sorry. So when I stay in this state and I see that the target state from this is 1 and the other is 2. Now 0, 1, 0, 2, and 3 are included in Y. But since state 1 is not included in Y and it's a target state from this state, it means that also 0 state must be excluded because that does not fulfill this property. While in state 2, the target state is state 3, and that is already included in Y. So pre of all for 0, 2, 3 excluded then 0, and then we have to look at pre for all of 2, 3, but that is still 2, 3. And I don't think I will motivate that more. I did that partly at least. It's the same reasoning as before. You look at the target state from a specific state, and if all the target states are included, then it's fine. And that is exactly what is the case here. From state 2, the only target state is state 3, and in state 3, the only target state is 3 itself. So yes, they are included, and you get the fixed point 2, 3. So in this case, it means that if you this expression is only valid in state 2 and 3. And once again, why is it not valid in state 0? It's because of this for all, because for all here requires that in all sequences that are reachable from this state, R must be true. And the problem is that you can from state 0 go to a state 1 where R is not true. So it's clear that state 0 does not satisfy this specification. But when you start in state 2, all the rest from state 2 and forward, they are included. So here is a repetition because in my lecture notes here, this was a new lesson. Let's see if this, yeah, okay. The only thing I will add now, which I haven't mentioned before, but I will do that quite quickly, is that now you can also combine these type of expressions recursively. So you could say, for instance, if you would like to evaluate this expression, always, for all sequences, always there exists a sequence such that finally you get P. Yeah, is this of any interest? Sure. It's actually what we have talked about very much in the course, and that is the non-blocking condition. The non-blocking condition is exactly described as in this way in CTL. And it's not possible to express this non-blocking condition in LTL, which is a defense for that CTL is useful. Okay, so if you would like to validate this expression, then you can do this in two steps. First, you validate existence, eventually P, with this mu calculus expression. And then the result of that you take as a new Boolean condition, and then let's call that Q, and then you evaluate always for all, always Q by a new mu calculus expression. And in this way, you can repeat this procedure and solve more complex problems. And here I show by an example how this can be done also in this case. But I think I leave that for you to take a look at yourself. I just tell you that, well, it's possible. And here comes some more complex examples. Here is one task I had in my last exam. First, we should motivate by why this automaton satisfies the LTL expressions. Always eventually P, where P is the mark state. Okay, what did this mean? Always eventually P. It means that repeatedly I should come to this state. And if we go around here, we can see that, well, if we go down to state 5, we can, yeah, the only choice we have to go back to 2. So that sounds okay. If you go to state 1, you can go back to 2, but you can also go to state 4 and 5. And from state 5, you can go to 2. So once again, we have a repetitive behavior of arriving in state 2. And if you go to state 3, you can also go back to 2, or you can take 6, 5, and then you have to go back to 2. So yes, wherever you are, you will be able to go back to this state, and it's actually no alternative, which there is no individual sequence where you can avoid to pass state 2. So you can guarantee that always, eventually, or repetitively, infinitely often, you will reach that state 2. On the other hand, not next P. Why is this not true? In that case, you could say that if you are, for instance, in this state 2, and the next, it's not valid in all the states you are. We can see about the comment here. Okay, the first part I have discussed, but then it says also here that from the initial state, the next state is 2, but also 4. In state where you are in... okay, sorry. I was a bit lost here. When I write expressions like next P, what I mean then is that I start in the initial state. And in the initial state, yes, I can reach state 2, and that means that next state is marked. But the problem is that the next state, another next state, is 4, and in that state, P is not true. So once again, LTL formula must be true for every sequence. So I start in the state 1, I get one next state 2, but I have another next state 4, which is not marked. And that means that not P. Next P is not true. Then we should show by mu calculus that the CTL formula always, for all, always there exists an eventually P. And that means that this system is non-blocking. And without going into all the details here, I show by mu calculus here. First, the inner part of this expression, namely this existence eventually P. And in that case, I take the mu calculus expressions for this expression, existence eventually P, and that was the set of states P union with pre-existence of Y. And if you iterate this until fixed point, you find that the result is all states 1 to 6. And that means that we can also intuitively verify here that from all states you can finally reach state 2. So that is what should be expected. I don't go into the detailed explanation here. Then you come with the expression that I call this existence eventually P for W, and then I know that for this W I have the set 1 to 6, and then the question is always for all always W, is that true, or for which state is that true? And then you have to evaluate that expression, and that translates to this set expression. Now we have the intersection of the set where Y, W is true, and we have the pre for all of a state set we call Z, which is the solution to this expression. And then we iterate this and find quite easily and straightforward that this also includes all states, this fixed point expression. So by this we have formally shown that by temporal logic and CTL that this non-blocking condition is true. So from the initial state of G, we satisfy this expression, and that can also be expressed that G satisfies for all, always there exists eventually P, meaning that the system is non-blocking. Finally, once again, maybe without giving all the mu calculus details, but just to show still an interesting example of how temporal logic and mu calculus can be applied. I could say that to implement these fixed point iterations in mu calculus is quite straightforward. So you find it confusing right now, but it's quite easy to implement those. A temporal logic supervisor includes all those states in a transition system that satisfy temporal logic formula phi. And then we should use mu calculus to determine a temporal logic supervisor automaton for the plant G given below here, which satisfies the following formula. So what this says is that, okay, there should, from the initial state, exist at least one path which always satisfy Q or R, and one where you have eventually P. And if we look at the initial state, we see that we can get to this state and where we have P. And also in this state, we can eventually, also in this state, we can eventually get P. And here we also have a state where you get P, and then you can repeat that. And then the question, do we have Q or R? Here we have R, here we have Q, here we have R, here we have P. So that's a problem with the first specification there. So probably we need to skip 4, but here we have Q. So it looks like state 4 needs to be excluded, and state 1 is also problematic, because if you go to that state, you will not satisfy that. Eventually you will get P. So by skipping state 1 and 4, we could expect to say that the rest fulfill this specification. And if you go through the details here, you will find that exactly state 4 and state 1 has been excluded, but the rest is there. So although I have to admit that there are some small peculiar details in the new calculus, it's actually a useful tool to synthesize more advanced specifications based on temporal logic. So by that, I would like to jump to the next presentation, where we will talk instead about hybrid systems and time systems. Yeah. Hybrid systems includes both continuous and discrete dynamics. And it has been quite popular since, well, it started around 1990 or something. We got a professor to our department, Bo Egert, who initiated this, and they found that he had been out in industry for some time and found that, okay, introduce logics into continuous time systems would be an interesting stuff. So that was good for me, because then I also did some early work, and my most cited papers are for sure on this hybrid systems, where we at that time analyzed stability of hybrid system by a specific computational tool called linear matrix inequalities. That gave some good response, definitely. At the same time, I realized that, okay, this is a very tough area, and it's not so easy to get financial support for such a tough area if you are looking for industrial support. Industry was not very interested in this. Now things are a little bit different, but it's still quite a challenging area. But we have found some interesting applications more lately. So I also went back a little bit more to this area, but for say 20 years I skipped any research on this. So I promise I will show you a nice video in some minutes, showing something which is an application of optimization of hybrid systems. That's the only video I show in this course. So after all these logical math problems and tasks, which maybe you are a bit tired on, I will show you some industrial relations and interesting results. But before that, let me give you some introduction to this area and to explain a little bit more what is a hybrid system mathematically. So what we do is that we introduce the continuous times dynamics in terms of differential equations. And the idea is then to do that in every, what we call location now. The automata have states. We have been used to that, but now we call the states locations. The circles here, we call them locations. And in these different locations, we could have different differential equations. And then you have a switch between these different locations. And the idea is that, okay, here one differential equation is valid, and in this location, another differential equation is valid. Yeah, I mean, there are different ways to handle this. For myself, I find it a bit unnecessary to express it so explicitly in that way. It's enough that we update some logical variables or some integer variables that, for instance, have one value, in this case, just the valve control signal U, either could be 0 or 1, open or closed. 1 means open and 0 means closed. So this is a logical variable. And in this location 2, U is equal 1, and in state 0 or location 0, it's 0. No, locations, sorry. In location L1, U is equal 0, and in location L2, U is equal 1, nothing else. Here we can also have guards on our transitions in the same way as we had for the logical variables. We could introduce guards and actions. The interesting generalization here is that now my variables could be continuous, and I could have conditions on continuous variables. And in this case, the continuous variable is the height of the tank. So when the height of the tank is below H0, then I open the valve and I go to this state, and then I get an input flow, and we expect that the height will increase. But then when it gets up to H1, you close the valve and you're in this state again. Actually, we had this example very early in the course, but then we focused more on this in terms of pure logical description. I translated, so to say, aside of the model, these conditions to events instead. So H less than H0, when that happens for the first time, I generated an event H going down. And when H pass H1 for the first time, when it crosses the border H1, then the event H up is happening. But now I would like even to describe the continuous behavior to get a more complete model. And what is the model for a tank? Well, if you have this type of simple tanks, you could just say that if you have a constant area of this tank, then the volume is the area multiplied by the height, H. And then if you take the derivative of the volume, you get, area is constant, you get A multiplied by the time derivative H, and that is equal to the difference between the input flow and the output flow. And in the input flow, you have this logical control signal U. So here you have the differential equation, and that is valid equally in these two locations, but the difference is that one of the signals, u, is 0 in L1 and 1 in L2. So this is the formal model of this system, and this is called then, a hybrid automaton. Yeah, I think I've said enough on that. Now it's interesting that we could extend this model by having a little bit more detailed description of the valve, because I mean the valve does not make a switch from 0 to 1 immediately. It takes some time, at least it's actually a ramp up or a ramp down of the valve. But now I simplify and say that, well, I give first an order, open the valve, and then after a small time TD, a small time delay, we say that the valve is opened. This is to introduce a simple dynamic behavior of the valve then. So an extended model including a time delayed valve gives us this description. What has happened here? Well, we have the change where we go from, we have the sensor or the guard when H is less than H0, then we should open the valve. But what I do here now is that instead I include a clock. I include a clock, and then I reset the clock, and when and then I also have a differential equation for the clock. Simply C dot equal 1 means that C increases as a ramp function, going continuously with speed 1 upwards. Then when the state variable C is greater or equal TD, then first I open the valve, put it U equal 1, and then you stay in location 3 until the H has passed H1, and then you start the clock again, and then you put the condition once again that when C is greater or equal TD, then you close the valve. So this is an extended hybrid automaton describing also the delay of the valve. So this type of model is very flexible. It can describe more or less every physical system. And on the other hand, we could be even more unified here. You remember that I talked about predicate transition models for logical systems with logical guards and actions. But now we can also add differential equations to this description, and we could include differential equations, even differential inclusions, as you see here, saying that, well, the derivative, the time derivative of the state variable xj, for instance, is at least 1, but not more than 2. So the derivative is in an interval here. It's not that common that we introduce such types of models, but it's possible, and there are, of course, applications where this is possible. You could say that it's some kind of robustness or uncertainty. In our model up, in our model up here, we could say that, I mean, if the gain factor of the valve is varying, I don't know exactly how much flow I have here. Is Q in a factor multiplied by the area of the pipe here, or what is it? So that's a way then, or you could say that different levels on this valve could also describe different values on this differential equation here. So differential inclusions can be useful. Then we can also combine this with the discrete guards that we had before, and we can even make jumps on the state variables, which is another interesting extension, that you can make discrete jumps in the state, even in the continuous state variables. And if you add this to the transition conditions, and in this way the differential equations, we can say that, well, what we have done is not much more than what we had before, where we had the simple or the only logical predicate transition model. It's actually only the continuous set with differential equations, which is the main additional part. Then you have set of initial states, and you could also have some marked states here. And even the synchronous composition here comes very easily, because what you only need to add here is the conjunction of, when you combine two systems, is that to combine the conjunction of the differential equations or differential inclusions in the two models. So this is a very, very general, but still quite a useful model, and I call it an hybrid predicate transition model. And of course, hybrid automata is just a special case on this. There are some invariant properties in the hybrid automaton, which I assume here are expressed by transition conditions instead. So there, maybe you could argue that, or some people at least argue that that is something I don't have in my model here, but that's a minor difference. Now, it's interesting that we can also extend our Petri nets to also include continuous dynamics, as well as, for instance, discrete valves. And this is a tank system with 3 tanks, and also a conveyor belt here with some vessels that we should fill by a pump here. And I will not explain the details of this, but it's just to show that it's possible to extend Petri nets to include also continuous time dynamics. One of my first PhD students also developed some things around this. It was actually his master thesis, but even himself, he was not very convinced about this. Unfortunately, we didn't publish a paper on that because we did some result already around 1990-92, which others have formulated after that. But yeah, that's life. So now I come with this video I will show you, and I think that's good to take before the break. So some background to this. Here is a time where I used to give some relations to high politicians. You know, around 2008, we had a big problem in a big crisis in the economy, and it was this bankruptcy in the US. Obama became the president, and he said that, okay, especially to the General Motors, and I think General Motors was especially in a very bad situation. And he said then, okay, I'm ready to support you, but you need to go for green technology and develop your cars in much more in that direction, which is interesting when we compare with when Trump became a president, and he made more or less the opposite. But okay, Obama's direction to General Motors was that okay, if you do that, I will support you. And then my group had collaboration with General Motors for some time, and they were quite positive and interested in our work on flexible production cells, robot cells, and so on. But so we had some projects, and they when they came into this crisis situation, they just had to cancel the collaboration with us, at least economically. Okay, we didn't get that much money, so it was not a big thing, but still, that was the situation. And then when Obama gave the message, then General Motors came back to me and asked, well, Bengt, could we continue some collaboration if you could do something on related to sustainability? And you see what I worked on I mean, all these logical things, and okay, we had some work on robots, sure, but I mean, it was not clear to me what I could do on this. I was just thinking, okay, I'm developing software. What does that have to do with sustainability? But we had some work on generating more smooth motions related to this mutual exclusion zones where we should avoid collisions. And based on that, the thought came up that, well, okay, maybe we could see if we could reduce the energy consumption of robots by generating better or reduced velocities of the robot motions. So I will right now show you let's say that I stop this and try to start the movie, and it includes some sound and music and so on, but I think I will, that's not the big issue. I will try to make some comments on what you see. And you will see first a KUKA robot. That's a German robot vendor, and they were interested in our work, and this was in an EU project later on, and in that case we generate first the trajectory with the ordinary robot controller. And then after that, we also show what the result we could achieve by using our optimized robot trajectory, and how much energy we could reduce, the energy consumption we could reduce. Let's see what happens here. Okay, so then I need to share again. So the project was called Areos, and Daimler and KUKA and others were involved in this. Here you see the KUKA robot in our lab, and actually you could see also here, you see the energy consumption, or rather the power consumption, the power peaks here during the scenario. So let's go in here. And then we have the optimized motion. And you see the energy consumption, see on the sound that it does not act so aggressively. Then you have both of these motions together, and you see it's not that big difference. here you could see some difference. But they stop exactly at the same time. And still we were able to reduce the energy consumption about 20 to 25%. So this was, you could say, from an industrial point of view, my most successful result. And I said that, okay, if there is anything that I have influenced the industry with, so is it maybe that part. At the same time, we could say that, well, robots do not consume so much of energy. So compared with the welding operations and so on, it could be discussed how much value it is in this. But still, Daimler, which is one of the really large car and truck companies, they meant, well, this is interesting, and Volvo has also later on shown a clear interest in this, and it's a little bit on this aspect that you know we all companies now want to go in the sustainable direction and tell that, okay, we are a green company. And that's also a reason why they are interested in this area. It's interesting that General Motors, they were not very impressed by our results. And okay, we could say that as long as we worked together with them, we didn't show any great results either. So, I mean, it took some time before we could really get this. It was actually due to a special facility in the KUKA robot, we could obtain this. So it's much harder for standard robots to obtain this. So now the question is, how could we do this? And the optimization around this is what I will tell you more about after we take a break. Maybe we could stay with 5 minutes break this time, and if you have questions, just go on.
Yes, thank you. So questions if you have. Oh, sorry. If you have questions, please. Yeah. If you have questions, please write on the chat box or unmute and you can ask.
Good.
You can take a break, Professor, till then.
Yeah. Yeah, should we start then again, or?
Yeah, I don't see any questions. If you have any questions, participants.
Okay, then let's see.
So one of our undergraduate intern did this energy optimization project around the same time, and he read your paper as well.
Okay. Yeah. Yeah, it's. I mean, there are. You could say that the background on this energy optimization was that. I mean, I was quite convinced that people must have been looking at the energy consumption of the individual robots for quite some time. Actually, not very many papers have published even on that, but I mean that could be expected. Our contribution was from the beginning mainly that we gave presented a procedure where you can reduce the energy consumption for a number of interacting robots. So that was a little bit more challenging. And there is where these hybrid automata comes in and so on. So then in the end, I mean, the practical good results we achieved was mainly still on the individual robot, that we could show that for exactly the same time unit, you can still reduce the energy consumption. And when we told this to the robot vendor, I said, "Oh, what are you doing? It's not possible. You cannot do this. What are you doing? Yeah. It's just some fake news." And so that was interesting. But after some time, they could realize that, yeah, okay, maybe we have some, some unnecessarily high accelerations. It's more or less all about trying to minimize the accelerations.
Yes.
And another procedure, and that's also related to, you could say, the interaction between robots, is that sometimes a robot has to wait before another has passed and done its work, and then it can go on. But to wait, it means typically when the engineers generate the robot programs, that they never think about any reductions of speed or quite seldom. So full speed and then stop. Yeah. And then stay there. Yes. Then full speed again. And of course, I mean, that's very bad from an energy consumption point of view. So that's why you should be more careful, and maybe if you should be there, start in 3 seconds. Let's use that fact and move slowly. So you are exactly at the border after at 3 seconds, and then you don't need to stop. You can just continue. And I mean, to stop and start, those are, we all know that the big parts of, or big contributions to the energy consumption.
To the energy, yes.
Yes, so those small pieces added together show that we could, it's a potential definitely to reduce energy. But more exactly how we did that, I will try to show you for the rest of this lesson if I go on then. Could I start?
Yes, you can. Thank you.
You should start the recording also. Oh, it's recording. Okay, sorry. So then I show you just, it's not an important contribution to our industrial results, but But the fact that these hybrid automata, which I introduced earlier here, they can also be used in this situation, or in this case, hybrid Petri-nets. So for quite complex situations, this hybrid Petri-net describes the behavior. But then we come to the optimization part. Okay, this is a system where we have an optimization including discrete decision variables. And here I really want to give a broad perspective on this right now, because what I have found, and of course I'm not, it's not only myself, but I don't see so many mention this complete picture I've written here, but there is a famous book on integration of optimization for systems including discrete variables. And that book tried to highlight the strong relation between constraint programming, CP, and operation research. It's a book written by Professor Tucker. And then, of course, we have discrete variables and we have continuous systems including time and energy. And within OR, we have methods like mixed integer, linear or nonlinear programming, MILP or mean-LP. I can already now say that the robot problem, energy reduction, is in principle a mean-LP problem. But then there are ideas within the OR but also within AI, like A*, local search, taboo search, etc. Constraint programming, which is especially suitable for logic expressions. And okay, typical applications in this area are planning, scheduling, and optimal control of timed, discrete event, and hybrid systems. So exactly what we're talking about here. Now, if you look at these three different areas, ORI, AI, and CP, they all include, okay, as said Ron, not Tucker, Hooker. In Hooker's book, he mentioned that there are three interesting parts or concepts that need to be combined to solve this type of problems. And that is search, inference, and relaxation. So what does search mean here? Well, you have efficient search methods like branch and bound, decomposition, A*, local search, etc. And you could say that branch and bound is probably from the beginning mostly developed in operation research, and OR is, I mean, you could say the main branch where a lot of these methods have been developed. But of course, there are also search aspects that have been developed in other fields also, like A*, which is a typical AI routine or method. You have also dynamic programming as a very basic tool here. Then we have inference, and that we say means that you try to reduce the search space. And in OR, we have cutting planes, and in CP, for instance, there are bounds propagation, logic deduction, etc. And here is an area where I would say that constraint programming and AI have maybe contributed more than in the other fields. And then we also have relaxation, which is of course a very important part. And relaxation, the most classical one, is that the integer variables, which we have in our description here, or in our problem formulation, they are then in classical OR replaced by reals. And Lagrangian formulation is also another example of relaxations. So you could say that all these three methods areas, they include different aspects of these parts here: search, inference, and relaxation. So Hooker's message in his very interesting book is that we should combine what we can learn from all these three areas within these specific topics: search, relaxation, and inference. Actually, there is a fourth method, or a fourth area, which I've mentioned, but not from an optimization point of view, and that is satisfiability solvers, SAT solvers. And there are specific tools, for instance, one called SMV, where they have introduced even continuous variables. So that they go step by step to extend the procedures from a computer science and logical point of view. And then there is a specific solver called Z3. And that solver includes also optimization. And that means that even these SAT solvers is a fourth way to solve optimization problems. And actually, we have used this SMV solvers, or Z3, to solve some typical scheduling problems, and show that this Z3 is sometimes very efficient, not always. I mean, it should be a surprise if a completely new method should be better in all situations, but sometimes they are better, and they are nicely competing with for instance, solvers within OR and constraint programming. There is a software called Groovy, or a package of routines called Groovy, which has more or less the most known methods. It's not a commercial method, so the software is open. So we have compared Groovy and this Z3 and found that, yeah, okay, there are definitely situations where also Z3 is better than the solvers in Groovy. What is more interesting in this case is that the logical variables are quite, they are not handled very well in the OR methods. It's something called big M in OR, which means that one introduce variables which are either 0 or a big integer value, say big M. And in this way, the solver has to decide, should I go for the 0 or the high value of this variable? And in this way, we can have a guarantee that you take either of two logical conditions, like true or false. This is a way to implement logical conditions. So alternatives, go in right or left direction, depending on if you should apply the big M or the 0 value. And this is not very good also from from a numerical point of view, because mixing values of high values could be quite disturbing for convergence and numerical condition point of view. But it's also, when you read a code with this big M and all your logical conditions are transformed to the big M, your code looks very messy and your equations are not very easy to understand. On the other hand, if you take these SAT solvers with their complete logical expressions, I mean, if it's an OR condition, you just write OR. And if it's a conjunction, you just write AND. So I would say that these SAT solvers and SMT solvers, they are much more readable code, and it's so easy for the students to formulate problems within this language, and in that way solve, maybe not always in the most efficient way, but definitely in a very understandable way, solve quite complex problems. So this was some advertisement for the computer science area within optimization also. So now we come with the introduction of hybrid systems, and then how should we handle this? And you could say that in all kinds of hybrid aspects, what we try to do is, of course, to make some approximations, and in optimization, including continuous variables, there is standard tricks available since 10 or 20 years. And that is that a continuous variable or even a continuous state vector is approximated by Lagrange polynomial. And then it's possible to sort of say exactly satisfy your continuous state vector, not at all times, but at specific time instances, TL, T0, T1, T2, T3, etc. And this Lagrange polynomial looks like this, and then you see that this L becomes it's a product of different terms. I don't think I will try to explain this in detail. The conceptual idea is that by introducing this, we only guarantee that you satisfy your problem in specific time instances. But if you do that, then what happens in between is most often smooth enough to get a good solution. So nonlinear optimization criterion results in a nonlinear LP problem, an NLP. And if we then also include the discrete sequences, it gives us a mixed integer nonlinear programming problem, mean LP. And what we have is the possibility to describe the continuous differential equations describing the, say, robot motions. And by doing that, we can also try to solve, together with the discrete decision variables, the mean LP problem. Now, this mean LP is still considered to be the most difficult optimization problem. So what we tried to do was to even more simplify this, because to solve a mean LP problem, including this energy consumption and so on, is quite tough, but before I come into more comments on that, I should also say that, yeah, okay, we also had some work where we integrated CP and NLP to get more efficient mean LP solvers. So to combine constraint programming for the discrete dynamics with NLP for the continuous part, that is an interesting aspect. And we have looked at specifically then 4 AGVs moving through an intersection without collisions, and integrated CP NLP reduces the number of executed NLPs by more than a factor 4 compared to ordinary efficient mean LP solvers. And by this CP technique, the added time of running the constraint programming routines was less than 10% of the running time for the algorithm. So you could say that by introducing some stuff from constraint programming, we have been able to solve mean LP problems quite nicely. Okay, now I come into what we did more specifically for this robot motions. The idea was then that, okay, the robots are from the beginning programmed to avoid collisions, to path around some behaviors or some parts, static elements in the robot cell, which you need to avoid. So we assume that someone has already generated the given path you should go from A to B, from one point to another. The only thing we would like to update or change is actually the velocity and acceleration. And then we simply formulate, we assume first that we record a given solution of the robot motion. And this was possible to do with the KUKA robot. It was able to even save data for every 11th millisecond. So every 11 milliseconds, we got the complete trajectory of the robot, all 6 axes. And based on that information, we try to see, could we reduce the velocity at some places, and then, of course, meaning that we need to increase the velocity at other parts, just to keep the total execution time. And here you then see that if we know the trajectory as some given time instances, we can express the velocity by an Euler approximation and the acceleration as the Euler of the velocity. So this was more or less what we did. But now the question, how could we take care of the optimization? Well, the idea was quite simple. Here we assume that we have the sampling period equal 1 time unit. Okay, that was 11 milliseconds in the KUKA application. Here I call it the interval just 1. That means that I have the scaling, my time unit is these 11 milliseconds. But then I introduced some freedom, namely that the first interval could be, the sampling period could be extended. So instead of having T1 equal 1, I could take that a bit later. And even T2 could be even more extended. So I get a new sampling interval H0, H1. And then you see that between 2 and 3, there where I typically have some lower velocity, then I could reduce the sampling period. And in this way, it should be able then to give more freedom to velocity. And then we sum up the square of the acceleration as a simple criterion, such that the sum of squared accelerations for all 6 axes were minimized. Okay, there could be some weighting factors between the different axes and so on. But what is this? This is a nonlinear optimization criterion that results in an NLP for each mode sequence. So I assume now that I only focus on one mode where we don't have any discrete changes of the variables. So it's only an evaluation of the continuous part then. Then if we include this procedure in a discrete sequences, that gives us totally a mean LP problem. Here it's interesting to, if we look then at what are we really interested in? Is it the acceleration? No, it's the power consumption. And the power is proportional to velocity multiplied by acceleration. So we have also tried that as an alternative criterion later on. And well, it gave just minor changes of the result, but a little bit better if you go for power and energy consumption as the real measure of when you evaluate on the final robot. But even the early phase where we just minimized acceleration worked excellent. Yeah, okay. Actually, here I see that I should have had one figure showing the typical results, but I can just tell you a little bit more on that. You saw the peaks in the movie, and then you could see that the peaks were drastically reduced. And you saw also in text that the energy reduction was reduced 20 to 25%. Actually, it was very critical to evaluate this energy consumption because there are some measures on current and velocity, and it's not. Yeah, it was first a problem just to get a true power measurement, but in the end we did that. But what was more interesting was that the energy consumption of the robot was not constant. We had quite different energy consumption when the robot was cold and when it was warm. So, but we had a very careful PhD student at that time, and he made very detailed evaluations. So we think that our evaluations are as good as possible, because what we did was that we made this, we solved this NLP problem. And that meant that we got, in principle, the different sampling periods as the modified sampling periods as the result. And then we simply could download that back to the robot and asked it to generate a modified trajectory. Actually, we had first to resample the trajectory, so we came down to the 11 milliseconds. So first adjust the sampling periods, generate the trajectory, and then given that trajectory in the computer, you could resample it by the 11 millisecond periods. So there were some technical but rather straightforward complications to solve. And my final comment on this is that, okay, we could reduce the energy, but even more the power peaks, because the power peaks are, they were very high, you could see in the curve we saw on the right lower part of the video. High peaks. And they are definitely reduced even 50, 60%. without making any specific minimization of that part. That came for free, which is interesting. So what we have done after this industrial work was that we saw, could we implement this in other frameworks or in other platforms? Because the KUKA robot, with this sampling mechanism and the ability to control the individual paths and trajectories in such a detailed way, is not standard. It's not possible, and it was absolutely not planned to be used in any industrial applications. But for us, it was good that they happened to have this. They call that the Hollywood mood, because for some nice advertisement and Hollywood applications of robots, or movie applications of robots, they wanted to have this extra freedom. But it was good for us. So what we have done after this is that we have also implemented these optimization procedures in more standard CAD software, which for robots, RobCAD, etc. And ABB has a special software called Robot Studio. And this Robot Studio, in that there is now a possibility to also measure the real energy consumption in the software. So based on that, we can make experiments virtually, so to say, and making evaluations and then optimizations, and then modify our trajectory. And the main modification is that velocities are typically, the peak velocities are reduced, and we try to avoid measuring the we try to avoid having stops in the trajectories. So any waiting for the robots, we try to avoid as much as possible. Then an interesting aspect on this is that there is actually a conflict between robustness and stability and energy consumption. And by robustness, we mean that, well, there are typically some slack in some operations, and from a robustness point of view, it's actually good to have those slack if there is an uncertainty in the operation time for O23. Maybe it sometimes takes a longer time and sometimes shorter. Specifically, or more common, that sometimes it takes longer time. And then, of course, if you don't have any slack in your system, you will get less robustness. On the other hand, what the energy consumption does is that it tries to avoid the slack, because here we have a waiting time. Why shouldn't O23 be completed before O13? It can go slower, and then be ready at the same time as O13, operation O13, and the same for O33. So obviously here there is a conflict between robustness, stability, and this energy consumption. So then we had an additional work related to that. And I don't make any detailed comment on the difference between robustness and stability. I have tried to explain what I mean by robustness here. That it's good to have some slack, and here we could see that here is the okay, here is this stability and robustness, and also we see here that we would like to be down here as much as possible for robustness and stability. And then we see that up here is the best energy consumption, and down there it's best. But up here we have much worse energy, higher energy consumption. So this is just a way to describe that. Okay, before we leave the area of hybrid systems, I just would like to show you 2 examples also on some modeling of this type of system. So this is a temperature situation where you could say that we had the level control before, and now we have the temperature control. And in this case, we have discrete flow sensors, one measuring low, medium, and high value. It's quite similar to what we saw for the heat control. So in this case, we have the continuous model, and you could simply go between these different stages here. I think I need to read this in more detail. Okay, the power is the control signal, and you have we have 3 different times constants and also static gains here, and they correspond to 3 different flow levels, low, medium, and high. So you could have low flow, medium flow, or high flow. And we only have a discrete sensor measuring this, and that is sensor showing low, medium, and high. That the switch from one level to any of the other 2 levels is always possible. And then we should generate a hybrid automaton for this continuous time system, including the discrete flow models. So the meaning of this is that these parameters, TQ and KQ, they have different values in the high, medium, and low location. So depending on in which mode or location we are, you get different values of Q, and that means different values of this continuous time differential equation. So this is kind of hybrid system. The next one is actually 2 robots that are moving around center, and there is some gravity, and you simply have, let's see here, the robots are to move through a shared zone. Okay, the robots are in this shared zone when the angle is between plus minus pi4 or 45 plus minus 45 degrees. So the problem is that we should generate a model here which avoid that they are at the same time in this area. And the robots, one is going from the top and going down, plus 90 moves through the zone and ends downwards. And the second robot has the opposite, moving from minus 90 to plus 90 degrees. And these 2 robots obviously need to share this path zone. We should then formulate this as a hybrid automaton, and you have the differential equation for the 2 robots here, and they should avoid this forbidden location. So each robot had 3 locations, one if it's less than I think it's it's a small error here. because it should be the opposite sign. But okay, we can say that here we have different zones. Here they are in the free zones. They are outside the shared zone, and here they are in the middle zone, both of them, and that should be simply avoided. So this is the middle zone where both of them are in. That is the combination that should be avoided. Some words also about timed automata before we end for today, or how is it? Yeah, we should continue one more quarter, yes. Or is it something, is it correct that we should go until 2:45? Okay, your time is of course different, yeah. Okay, but we have one more quarter. Okay, I'm going on. So for timed automata, that is a special case where you have the simple differential equation for clocks, which the time derivative of the clock, of each clock is equal 1. So that means that we don't need to have explicit differential equations. We just assume that we have a set of clocks, and these clocks are then used to specify specific properties. And I will show you now soon my optimization problem, which I've looked at the last month here. And well, in the end, I came up with something I think can be of interest. So all the, yeah, okay, here I have even three models with local properties on, in this case, I use even 4 clocks. So we could say that the first one is that G1 should have an operation which takes at least a time unit T1. And it has a second operation that takes at least a time unit T2. And then we assume that each of these operations have individual clocks. So the idea that before you start a new operation, and you need to count a specific time T2, then you need to reset the clock corresponding to this. So but when you make the transition from state 0 to state 1, that can only happen if the time has passed T1, if the clock C1 is greater or equal T1. And then we assume that you make the transition as soon as possible. So that means that in practice, the transition is taken exactly when you get equality here. But there could be also logical constraints or conditions saying that, okay, the C1 could also be constrained by another constraint, and that means that in practice you will not. It will take some time, extra time, before this condition is satisfied. So this is an absolute condition: C1 equal 1, T1 or greater than that. But say that there is a other condition that C1 should be greater than T5, and these are synchronized, then this greater or equal is a necessary condition. But especially for optimization, we try to make all these transitions as soon as possible. So here you make this clock reset, as it is called, and then you start the next operation, and when the time has passed there, when C2 is greater or equal to T2, then you are done. And in this case, we put a logical condition that a logical variable C2F is equal 1. And then for the second operation, we have another clock, C3, which need to pass time unit T3 to complete that operation. So when these two operations are satisfied, then we start actually fourth operation. And that is only allowed when the two first are completed. And that means that both C2F and C3F are equal 1. And then you reset the fourth clock and start the operation, go into this state. And then when C4 has passed T4, then you are done, because then all are in the final marked states. So this is a modular description of saying the same for this. And here you see that you get possible ways to go through this. It could, depending on what T1 is, and T2 and T3. It could be, for instance, that T3 is very short, that this operation is short. Then it means that you go this way, and then you have to wait for C1 to make its 2 operation before you can go on with the last operation. But it could also be that C3 is longer, and then it means that the first operation in the first system can be completed, and then maybe C3 will be completed, or even C2 can be completed before C3 is completed. So all these combinations are represented here. So this indicates that it would be interesting to formulate modular descriptions for this to obtain a more flexible and a model which can be reused in many situations. So this was exactly what I proposed in my paper here. And here is a formal description of the timed automaton, but I will only make comment on the graphical part here. But you could see that the timed automaton has a very similar structure to what we have seen before. It's what is added is the set of clocks, and for the rest there are some specific guards and restrictions on the clocks that are included in the transition conditions. So a transition condition is that you are now in a location L, you make an event A, you have some clock constraints described by phi, and then you go to the next location L prime. This is exemplified here. Start in state 0, go to state 1, and then the clock corresponding to, I is equal 1 and 2. So let's assume that I is equal 1, G1. If C1 is greater than delta 1, then you can make a transition from 0 to 1. And in that case, we also have an event A1, which means that this model can be synchronized with another system, which also want something to happen at the same time. Then this clock C1 is reset. It says here that the next value of C1 should be equal 0 after the transition. So when you're here, you know that C1 is equal 0. And then you can start to calculate or execute the second operation, and that has a duration delta of 1 plus 2 delta 3, and that was duration delta 1. Then you can apply this for I equal 1 and 2. So what happens now if you combine this model where you have a delay before you start an operation and the duration of the operation? When you synchronize these two models, G1 and G2, well, then you get this pattern, this model. There are no shared events here, so it means that it's just an interleaving. Okay, this is 16 states, sorry. Well, that's not so problematic maybe. But the problem is that there are actually a number of clocks here now. And depending on which route we take, which path we take, we will get quite different results of the clocks. And this will also determine how long time it takes. Just take, for instance, going from 0 to 5. Then the condition is that, okay, C1 must be greater than delta 1. And then you come to this state location 4, and then it said that C2 must be greater than delta 2. But note that C1 and C2, they are 0. They are, so to say, started in their 0 with 0 value. And so there is no initial reset. I assume that they are 0 when we start. Now, if delta 1 is larger than delta 2, say that delta 1 is 3 and delta 2 is 2. Okay, then you have to wait 3 seconds until you reach state 4. But then the clock C2 is already, both the clocks start here, and they are both equal 3 because the first operation, delta 1, took 3 time units. So the clock C2 is already 3. But delta 2 is only 2, so 3 is larger than 2. So immediately we jump to this state. While here we have the opposite. First, the second clock should be evaluated. And then here you have passed 2 time units. And then you have to wait here 1 time unit before you come into this state 5. And here, actually, they will both arrive in the maximum of, at the time, which is the maximum of delta 1 and delta 2. But if you continue here, there will actually be different results on these clocks and also different time units for going between the different states. And that means that depending on the path, the road you take here, you will get quite many different make span or total time. And here comes the optimization. We simply want to find the best route to go through this system. And I tried to estimate or more systematically evaluate all these different combinations here. And unfortunately, I haven't written any software for this, so I made this by hand. And my conclusion was that it's between 26 and 30 different states if you combine the locations with the different clocks. So, I mean, this does not give you the complete picture, and you must, in principle, all evaluate all different paths passing these different combinations of location and clock values. So then, of course, it would be nice if we, for this situation, could say something which is more reduced, and that is what I came up with in this paper. Because I mean, always when you realize the solution, it's very simple, because you could say that the optimal solution for these two, when you combine these two models, is that you take the maximum from the maximum time from 0 to 3 for the first, and compare that with the maximum time for the second model. So delta 1 plus delta 3 or delta 2 plus delta 4. The maximum of those two is the optimal time. So when you know that, you could also evaluate and see that, well, okay, in this case, it's actually enough that you either, let's assume that delta 1 is that greater than delta 2, as we had in the example before. Then you will take this route, and then you will start executing A2 and reset that clock, and then C1, which delta 1, sorry, we said was 3. So here you have passed 2 time units, you reset, and here you have passed 3 time units. And then it's enough that we evaluate that both the second clock in the respective models are have passed their limits, delta 3 and delta 4, to reach the final state. So you could say that the time optimal solution is represented in this not very much smaller model. It still has 9 locations, but the clocks here, you don't get a huge number of different clock values here. So either you go in that direction or this direction, and then the final evaluation is very quick here. So you go in practice, you could say that you reduce the search dramatically by applying this model. Why having a model if we are looking for the optimal solution? The idea here is that, okay, this model can now be used combined with a number of other models which you could synchronize with. So I'm soon finished here, but just tell you that here I have 5 different models with some initial events, and some of them are related to each other. For instance, that this third model says that, okay, I must first pass the time delta 3 with event B before I can make an A in the second model, because here I have a shared A between the third and the first path. So there, now I've introduced some additional restrictions. And in this case, I also have that D is restricted. D cannot start before G5 has passed this state 2. And then if you then combine these 5 models, including this result, and with a slight assumption here. First, combining G1, G2, G3 just gives you this short model, and then you add the other 2. And if we, just to save space here, I assume that now that delta 3 is less or equal delta 5, then I get this final solution. So this is quite much of a reduction compared to the original system, where just taking 2, just taking the 2 first models. Well, okay, I had some additional time delays in the other one. But okay, let's say these 5 models includes definitely a number of complications. I don't know exactly how large the state space would be to make a complete search on this. But I showed at least that this combination can be reduced quite significantly. And it's interesting that this behavior comes up, and it was a coincidence, I realized when I formulated this model that down here, that I could actually use the results I obtained in the first to optimize the combination of this and the minimization of G3 and G4. Then I could use the former optimal procedure and come up with this solution. So what I've done now is actually only analytical problems, and of course, is that really useful for big complex systems? Well, the interesting thing is that every reduction you can achieve still gives some contribution to the reduction of the complexity, because even if my systems does not have this simple structure, if you can simplify them and some parts and avoid some of the search space by this type of local minimization, it still can make a significant reduction of the total search. And what comes here is my final slide. That is could generate a dramatic reduction, actually. And that is when you have alternatives. No, sorry. When you have just a few of local behaviors, we assume here that these two choices are not synchronized with anything else. So this is a local choice we make in this system. Then we could look at individually, what is the fastest way to go from A0 to A and from A0 to B. And we see that from A0 to B, it's just that we first have to pass delta 1, and then we reset the clock, and then delta 4. So it's delta 1 and delta 4. When the clock is greater than that, you should be able to go to this marked state. And here we have to state 5, we have the reduction that, okay, either you can take this route, delta 1 plus delta 3 or delta 2, and then I immediately get into state 4, and then the final reset, and you're in state 5. So this system can be actually reduced to this model, where I still have a timed automaton here. I have a minimization from delta 1 plus delta 3. And I take the shortest one here. So the clock needs to be the minimum of delta 1 plus delta 3 and delta 2. Then I have the, so to say, optimal route. Take the left choice, and here is the right choice. And this type of reduction, where you can join a sequence of local events, is what I argue is the most important reduction in this paper. It's an idea which we formulated some years ago, but now I try to make it a little bit more formal and looking into some more combinations of this with also these other minimization, where I also have some events that are also shared with other parts. So this is a combination of optimization with shared events and optimization with local events. And we can say that when we only made optimization based on these local events, we could show example with an extreme reduction. But of course, this is not possible for all kinds of systems. But it gives at least an indication of what abstractions can do also for optimization. Okay, so by that, I stop here for today. Any questions?
Thank you, Professor. There is a question perhaps by Dipojwal, yeah, on the chat box. Yeah.
Okay, let's see.
She was asking on our web. yeah, on a slide.
Yeah. How do we implement this automaton model with constrained description, like through programming or simulation or using equation solvers? So now I would like to ask you what you mean by with constrained descriptions. Okay. Constrained descriptions, which, you know, I presented some parts here, 50. Yeah, okay, so you wrote it now. So which one, was it around this timed automata you were thinking about? Or can you, with these constrained descriptions, what did you mean by that? I guess that you tried to write something, or could you speak out? Otherwise, I tried to...
Yeah, Deepojwal, can you please speak up? Yeah.
So this was not my question.
So this is what you have written here. While he was presenting on a slide, he was discussing about, you wrote, I don't know, is this the only set of please read go through the...
Yeah.
So I was asking in that slide for the timed system.
Yeah.
So were those the only set of subautomatons that were possible given the global model? Like, and is there any rule or algorithm to construct the local models given the global model?
Aha. Oh, yeah. No, okay. Now I say like... Okay, so the idea is rather the opposite. So let me show you the slides again, and we can discuss around that. So I share my screen again. The idea is that we never should construct the global model, because we normally could start with local clock models. So if you have this time system from the beginning, which we could say describes more or less similar situation where you have, for G1 you have 2 operations, and for G2 you have a 3rd operation, and for G3 there is a 4th operation, and all of them have time limits. What I write here, that as T1 and T2 and T3 and T4, they corresponded to this delta 1, delta 2, delta 3, etc. In the other presentation. So my assumption is that you have from the beginning modeled your system with in this way of as local models. And you could say that, I mean, if you have a system with a number of operations, all of these operations are in sequence or as alternatives or in parallel, etc. And they can then be described by simple operation models, and then the joining of them is described by introducing shared events, etc. So of course there is a modeling feature here which I didn't emphasize enough. I realized that. So this is, I mean, a real example could maybe have, say that you have, I mean, you can have up to 100 operations. Maybe that's, yeah, I mean, sometimes it could be any size, but you could at least expect 10 to 20 operations or something like that. Those operations could be described by this type of small models, as I show here, for this G1 and G5. And in that case, it could be that you have actually one timed automata for each of these. But at the same time, it's actually better if you already know that, well, there is a clear sequence of operations, and then you formulate that just as a direct sequence. First operation, second operation, third operation, fifth operation, etc. But then, if many of these operations are local with no constraints related to other operations, then you can reduce them immediately by the technique I showed you on the last slide. Let's assume here that, for instance, I have 10 operations. It should mean that I have, say, reset, time constraint, reset, time constraint in a sequence repeated 10 times with different time delays for the different operations. And they can just be shrunk down to one operation with then delta 1, delta 2, sum of delta 1, delta 2 up to delta 10. And that is condensed and abstracted to just one operation. Of course, that sounds maybe, it's intuitive, very clear, but then one could ask, is this really of practical interest? And well, you could say that maybe these operations have some coupling to other parts of the system, but it does not have coupling to all other parts of the system. So at least you can, from the beginning, reduce something, and then when you synchronize some of these models together, you get more of local events, and then you can make further abstraction. I hope that helped you a little bit to understand this.
Yes, sir. Thank you, sir.
Okay. Any other questions?
So you were reading some other question, perhaps that's what Deepojwal said, that was not his question. Anyone else?
Yes,
who would
ma'am.
like?
It
Yeah.
was my question. Hello, ma'am.
Okay.
It was my
Yeah.
question. Yeah, I just repeat my question, sir. I just want to know that for different, like we generate the different state sequences corresponding to the operations of a plant. Okay, and then we carry out certain reduction techniques, and then we synchronize the various types of operations under certain constraints, like we have given the time delays, or we have set the clocks according to synchronize the operations, and we sum it up. My question is that do we solve these state sequence diagrams using the programming modules, or we are solving it using certain equation solvers? This is my question.
Okay, fine. Yeah. So yes, my comment on this is then as follows. You try to make as much of reduction as you can do by this technique. And you could say then that, okay, it could be that you even use algorithm like Dijkstra, which is a standard shortest path algorithm if you have a number of local events here, but you could also say that I mean, very straightforward search and breadth for search could be implement this local reduction. But then of course you come into a situation where, oh sorry, I cannot make any more reductions, and then you should use any good optimization method to take the final step. And then, of course, you can use mathematical programming like mixed integral linear programming, or you could use constraint programming or any other preferable method, as I indicated earlier in my presentation. So you could say that this abstraction is sometimes something you do in the beginning of your search, and you synchronize models, you make further reduction, and you go on. And but in these different steps, when you make the reduction, you could also have use of, say, Dijkstra's algorithm. And in our implementation so far, we have used this reduction combined with simply Dijkstra's algorithm. But I mean, there are other methods that could be more efficient, like combining branch and bound relaxation, etc. So the focus here is just to show the potential of this reduction for optimization. And I have to say that we had an expert from mathematical optimization for my PhD student in the committee, and she was quite impressed about this reduction principle. And I asked her also if she has seen something similar, and it does not seem to be very similar, exactly similar method. But okay, I mean, abstraction and reduction, all people talk about that, but that can be done in different ways. And one thing here is important, that we don't make any approximation at all. If we succeed with this, we get the true optimal solution. But of course, this can be combined with a lot of other methods.
I understand it. Actually, when I have gone through your lecture contents, I have seen there is an optimization of the hybrid models. I actually working in the optimization techniques. So I'm working with the various programming techniques like Lagrange multipliers, or we can say the Newton-Raphson. These are conventional techniques as well as the non-conventional techniques. Yeah. And when I was going through your lectures, and I was just correlating it, that these abstractions and reductions, these optimization means somehow we are relating it to the operation research. And exactly today you use that word, that in the operation research such type of optimization is done, and now correctly correlate that using the some type of assignment models, or we can say shortest path routings, we can carry out these reductions. This is a one part of a problem, and then by finding out by understanding the behavior of the variables which are participating, then we can carry out the planning or scheduling by using the conventional or non-conventional optimization programming techniques. Am I right, sir?
Yeah, I'm not sure if I understand, if I could follow all your parts. I mean, you are using methods which yes, we are familiar with, and of course every one of us, even if we are using methods, we are trying to improve them. So it's, I mean, the whole operation research area, they are working on, in some sense, established methods, but they improve them all the time. And of course, introducing new elements. To be honest, I haven't seen much of results where you had these modular systems with their timing behavior, and you synchronize them, and then you get more of local behavior, and you try to use that to make further abstractions. That's my contribution. And I think that in your case, if it's something similar to the models I described here, you could probably combine these methods too. Yes.
Yes, I'm doing the second part, that I get the values of the, I identify the variables, I identify the behavior of the variables, their constraints, and then I use the conventional or non-conventional optimization techniques to find out the, we optimize the objective function relating to those variables. That is my second part. But I just definitely, yes, I got fascinated by this first part, that we need to create the state sequence because we have some type of a problem. I belong to the electrical engineering as we can say by background. So we have such type of problems in electrical engineering, and we can also go into this type of the, we can say, implement the AI techniques to generate the state sequences, carry out the certain state abstractions and reductions, and then we have to implement the optimization model to find out, to optimize objective function. So that you given me a very good idea to implement a certain type of a problem in the electrical engineering. Thank you so much, sir.
Yeah, thank you. Thank you very much.
Thank you, ma'am.
And I could also say that, I mean, this is an area which is rather new for myself. And to these abstraction techniques, which we are familiar with from the computer science area, and pure logical systems, that does not include any optimization at all. It's just to reduce to something that in the end typically just brings you down to 1 or 2 or 3 states or something. I will discuss that a little bit more tomorrow. That is a field we have worked for many years. But what my idea, and especially my PhD students' idea, was, why couldn't we also apply those kind of reduction principles and include optimization? So this was a way to boil these two areas together. You know, I haven't implemented anything of this yet. And I really see that there is a big potential to do more on this. Yes.
Well, good discussions. And anything else that anyone else would like to ask any question? So if not, then we request all of you to please start your videos so that we can take your pictures. And I request Shubhangi to please do this on my behalf. Thank you so much, all of you.
Okay, and I thank you and see you tomorrow.
Yeah, thank you so much. Thank you so much, Professor. See you tomorrow.
See you.
So thanks all the participants. As we see that it's already 6:39, 6:40. The next session we had planned was 7. If I reach home, I don't know if I'll be able to start quickly with the 7 p.m. So can we start at 7:15? I'll hardly take 45 minutes to tell you how we create a new, can use a neural network system for some data of some data for control systems. That's so 7:15 will be okay for you all. I think so.
It's okay, ma'am.
Okay, thank you so much. I'll be rushing home and then we'll be meeting. Fine. 7:15 we are meeting. Fine, thank you. So Shubhangi, I'm leaving a meeting.